Can you hear me? Everyone? Let's see that. So. Wait. Can you hear me, everyone? How about those on Zoom?
Yes.
Okay, perfect. Thank you.
Yes.
All right, thank you. Okay, so with that. All right, so what I would like to do today is to start solving a design problem using the Smith chart. And we're gonna do this from now on until the end of the semester, right? So try to design using a combination of equations and the Smith chart, whatever it's easier. So you will see here, usually the Smith chart is best if you feel comfortable using it. It's the easiest way to do a design. So here is a problem, all right? So I will read it to you. You have it also on Canvas. And it says here we have a source. I'm giving you the source in the time domain. It's a harmonic source. So you know immediately we are going to solve the problem in the frequency domain. And for this source, I give you the amplitude of the wave, which is 1 volt. I'm giving you the frequency, F, which is 10 gigahertz. And what it says, we have a source with an internal impedance at 10 gigahertz equal to Z. Okay, the source now has also an internal impedance, Z sub S, that's how we normally show it, 50 ohms. So it's a real, you will see also here. And so at the end of this transmission line, we have a load. So practically what we want to do is to connect the load, which is an antenna. All right, so the load is here. We want to connect to the source. And of course, they are physically separated. So we have to use a section of, we have to use something to connect them. All right, so it's going to be a transmission line. That's what we use to connect a load and a source if they are physically separated. And so I also give you the load is an antenna. And at that particular frequency of 10 gigahertz, the antenna has an impedance, which has a real part of 100 ohms and an imaginary part of J30 ohms. All right, immediately from that, we see that the antenna is inductive. Okay, so it has an inductive component. Okay. So 3 questions in this problem. Number 1 question. Can you match the antenna using only a transmission line? We don't have to answer them now. I'm gonna show you the process by which you have to follow these solutions, because this is the best way to organize your solutions anyway. Okay, so that's first question. Can you match this second question? Can you match this antenna using a transmission line and a lumped element? Now, when we use the word in distributed circuits, all right, when we use the word lumped element, we mean R, a resistor, a capacitor, or an inductor. Because as opposed, we call them lumped element as opposed to distributed elements, which is the transmission line. All right. So anything that involves a section of a transmission line, because they have a dimension, they're called distributed elements because they are distributing physically. And all of the traditional R, L, and C, we call them lumped elements because in a distributed environment, there is just a point, all right? So they're all concentrated. So this is the terminology that people are using to understand each other. Okay, and then, so that's second question. And then third question, I put four, whatever. A third question will be, can you match this antenna using a transmission line and a stub? And if you remember, the stub is a section of a transmission line that is either open at the end or short. That's what we call the stub. So you remember now the following definitions, which are important. The stub, you remember what it is, you should remember the lumped versus distributed, all right? These are some things that we are using. Okay, so now what I always want you to do when you try to solve a problem like this, whether they give you a schematic or not, I want you to develop your own schematic. It's extremely important because if you try to develop your own schematic on the basis of how you understood the problem, not copy mine, develop it on your own on the basis of the problem that I gave you. Here there is no, obviously you have to do it, but sometimes I will give it to you, or many times. If you try to develop the schematic yourselves, then you realize if there is a misunderstanding that you had, you will see it when you try to draw it, all right? Then you're gonna realize, even if I have a schematic, a lot of times you look at the schematic, you think you know what it is, and then you go and do something else. So you will have to draw it, that's number one. And then what you would have to do is put down the important parameters. Always, when you have a transmission line, always indicate the input port, output port. A lot of times you will see me placing here some dotted lines because A and AA prime physically are collocated, all right? They are almost next to each other. B and B prime physically are collocated. Why I'm saying that, you will see it in the solution. Why because sometimes somebody asks me why I placed here a dust line. Because to show that on a schematic, they are going together, right? All of the points on the line are going like that. And then at the end, you have this load, you put this there. Transmission line, you say, you put this a best what you have, this a best. And then I asked you to use a transmission line, but if you notice, I did not mention anything about this, and I did not mention anything about the line. So just from the get-go, you know that in this problem, in addition to whatever else I'm asking, in this problem, I already have these two parameters I can use. And in design, that's what happens, all right? This is called architecture, all right? The architecture of a circuit is when you say, I'm gonna put my load there, I'm gonna put my source there, I'm gonna use this, or I will lay out like that. That's architecture. But the next step, after you decide to have this setup, all right, the next step is to start designing, to start defining the specifics. That's called the design problem. So it's architecture, first of all, when you set it up. Then it is design. When you start, you have to define those. But to define those, you have to do it, not arbitrarily, but you have to do it in a way that satisfies the conditions of the problem. And what is an important condition here? It says here, we have a source, okay? And all of this with an internal impedance. We want to connect this source to an antenna. I don't see anything like that. But what do you imply when they tell you I want to connect my source to the antenna? Won't you understand that whatever you do, you have to make sure that the maximum power from the source goes to the antenna? Is that not understood, or somebody has to tell you that? Yes. I don't have to tell you this. Don't tell me, oh, you cannot tell me that I have to match it. Because why you would waste AC power that is so expensive to make, produce, and then you waste it. That is not all right. So the matching, so attracting most of the power from the source you design and took you time and money to move it to the antenna is a thing that you have to know. You are going to be expected that you will know that you will design your circuit to put most of your power that you have produced out for use. For example, that could be the source, could be the result of a transmitter. So behind the source, which now is simplified, you could have all kinds of things. You could have a source that you design, a power amplifier that it was even more difficult to design, a encoder, which is like it takes your harmonic, the carrier, and then puts all of the information and everything else, and then eventually you have to radiate that. So here on this, my antenna is outside somewhere underneath it, all right, here, and my transmitter is somewhere not exactly where the antenna is. So I have to take the power from the transmitter to the antenna. Don't you think that you have to get the maximum real power you can? If you don't think that way, then you are not appropriate for the design, all right? So always designers want to optimize power transmission. Okay, so, but here I help you with this. In fact, in reality, in a true designer will not have these questions. But obviously for our class, we are learning. So I want to help you think different actions that need to come in mind. So the first, you remember what I told you? In design, you're not going to create your own designs. You're going to think of what other specific designs people have done. Can you use them? All right. So one design that we've learned was the quarter wavelength transformer. All right. What did we say about the quarter? It always matches something, but it matches what? A real load, all right, to a real internal impedance of a source. So if the antenna had only a real power, 100 ohms, then we would be able to use a quarter wavelength transformer. Do you agree? On the basis of what we learned, what does a quarter wavelength transformer do? Do you remember? How does it work? Who is going to tell me? Here, I'll do it in a corner and then I will erase it. If I have a source here, well, let me use this one because, okay, let's assume that I have a little source, 50 ohms here. And then I have my antenna here, 100 ohms. In fact, I will not do it like that. I will do it like this. Okay. So what do I put in between if they are at a distance and I wanted to place something in between to connect them? What can I use? Yes, and what do we call this transmission line? We call it the quarter wavelength transformer. Why is that? Do you remember? Do you remember the name? Have we talked about this before? Oh, okay. So the quarter wavelength transformer what is it? It's a section of line which is a quarter of a wavelength and which has characteristic impedance Z1 to be the square root of 50 times 100. Do you remember that? That is it's a section of line. We've done this last week. So remember it. Quarter wavelength transformer is a section of line that always matches a real load to a real internal impedance. All right. So to have the maximum power here from the source going into the transmission line, to have the maximum power going here, what do we need? We need to have an input impedance there, to be 50 ohms. Do you remember that matching condition? You remember conjugate matching? Even we have it for complex internal impedances, all right? It's conjugate matching. When the internal impedance, Z sub S, becomes real, the only condition, the only time when you get maximum real power going from here to inside here is if this input impedance at this point is 50 ohms. That's the only time. So we have to make this point 50 ohms. Then from what we've done in the past, we've learned that if we have a quarter of a wavelength line, we call it quarter of a wavelength transformer, then, and if we select Z1 to be this, then we get here 50 ohms. So by selecting Z1 to be the square root of the product of this, we get that. Let me see, I wanna also point you to the place where we have talked about it. So you can go and review it, it's extremely important. So one problem with transmission lines is that everything we do built on a previous. If you do not review the previous lectures, it's gonna be difficult to follow and even more difficult to learn. So if I go to, let's go to modules. We go. Okay, let's look at previous week. Okay, this is various reactive. Here, remember when we saw that? This is the quarter wave transformer. Yes.
Why a quarter?
Because that's what it comes out of the solution. Here, we in this particular case, when there was a reactive load, it comes out of the solution that it has to impact, we even solved it with a complex load, all right? That it is a quarter of a wavelength, it is only under this condition that if you get the input impedance here, and you have this Z1, and then you have this length, that the input impedance at this point is Z0. It comes out of the equations of the transmission line. And it is in the book too, all right? So it's not, we found it, we write it here because I want you to remember it. We are not gonna prove this all the time. I want you to remember it, but if you wanna know why a quarter of a wavelength, go through the derivations we have done, and I believe also we did them in a previous. So you go, that's what I'm saying. In this, you will have to build on everything before. We don't have the time to repeat things. So from these equations here, all right, at some point, let me see, in the previous ones, you have to have important equations of lossless. Okay, let's see this one. This is the one, this is the solution. Okay, and just look at the previous week, all right, or what we covered. And also, terminated transmission lines. We have 2 weeks on transmission lines that we've covered before this one. Okay, 2 weeks of material. So please prepare, do reviews. Oh, why is that? It's all of the previous week. We have the lectures. Okay. I don't know. Can you see it on this? I don't know for some reason why I cannot get it. Download. I cannot download it. But in any case, what I'm telling you, if you look at the modules, okay. No. And I don't want to spend my time on this one because we're not going to cover anything today. And I'm anxious. All right, if you go into the previous modules, you're going to see towards the end, we have 2 weeks, 2 weeks. Module 12, and not in fact, it's module 11. All right. Module 11 and 12, we are talking about transmission lines, and we have covered it there. And so please review these 2 modules because we cannot repeat things that we have covered and then move on. All right, so the quarter wavelength transformer is this one, just to remind you. All right, it's a section of line that connects 100 to 50 ohms. Now, if you need longer than a quarter of a wavelength, then you have add multipliers of this. So it could be 3/4 of the wavelength. All right. So this one here, can be any like 3/4 of the wavelength and can give the same result. 5/4 of the wavelength and so on, if you need longer lengths. But usually if you have flexibility, you're gonna always go for the shortest length. But if you need longer distance, if the shortest length cannot bring the source to your antenna, then you go to this one, but it gives you this result. All right, so the question that we have first is, can you match this antenna using only a transmission line? All right, so that's number 1 question. But before we go there, you remember what I told you to do? I did this here as an example, but you set it up first. You put this one next. You always need to remember that this is resistive. And then you have a resistive and a reactive part. You need to put them explicitly. And then what I would like you to do, at least in the homework, is to make 2 tables, what you know and what you do not know. Because you're going to get totally confused and you're going to try to find something that you already know, right in the beginning, or you're going to think you know something which you don't. So what I will do is this: remember what is your design frequency, and then with this I will also remember the wavelength. Then this is the amplitude of this. Then this is the source input impedance, is real. All right, so I'm writing down. Then this is, which is inductive, it has a positive part. Transmission line has a beta, which I know, but I don't know Z naught. All right, so unknown parameters. Transmission line, I do not know Z naught, so I have the flexibility to define it, and I do not know the length. These are 2 things I can use. Lumped elements. What do I mean by lumped elements? Is it an R? It could be an R, so you have to select. If you say yes, you would have to select, is it an R, is it an L, is it a C, or is it a combination? Any combination of this is a lumped element, all right, because it's like lumped. Stub, because I made reference to that. The stub is a section of line that can be either open-ended, but you have to specify if you decide to use it. Am I going to use an open end? And if I do, what is the length? Stub. Am I going to use a short length, a short circuit? And if I do, what is the length? For this particular for this particular problem, I created this so it's easy for me every time to remember what I'm looking for and what I have in hand. Okay. So now after I do this, I'm going to answer the questions. Okay. So can you match this antenna using only a transmission line? Because ZS is 50 ohms, to match the antenna to the source, we need to make the input 50 ohms for the, as we have talked about, for maximum power transfer. To transfer ZA to 50 ohms, we cannot use only a section of line because the input impedance is not real. So practically, to only use a section of line and achieve this matching, and that section of line is going to be a quarter wavelength transformer, you only can do it if the antenna or your load is real. So what is the lesson here? The lesson is that if you have a real load, any type of a real load, you can always match it to a real source, all right, a real source, meaning the real input impedance, internal impedance of the source with any time for any value of your real load with a quarter wavelength transformer, period. So whenever if I give you a problem in the final and tell you, you have this kind of antenna, this load, I give you a real number. And then I give you the internal impedance of the source. It does not have to be 50, it could be 100, it could be 80, whatever the source is designing. Then you can always find a transmission line of a quarter wavelength or higher quarter wavelengths to be able to match it. But when you go to higher quarter wavelengths, only add multipliers, not even. 1/4, 3/4, 5/4, all right? Okay, so the answer to question 1 is no. With this one also we remember the what I told you about the real loads, how you can match them. So now, second question. And this one so far, even for the second question, you do, this is more like conceptual understanding, all right, rather than actual yet. But in the second question, I'm not going to the Smith chart unless I have to. So the second question says the following: can you match this antenna using a transmission line and a lumped element? Let's think about it. So I put down what I have clearly, all right? That's why it is important to know what you have. And now I say, okay, I just said before that if I make at some point this one real only, then I could immediately use a section of line, quarter wavelength transformer. But this is complex. So how can I make it real? What kind of element can I use next to it to make it real? Capacitor. Whenever you want to cancel an inductor, you cancel only an inductor, an inductive load with a capacitive load. So if I could put a capacitor in series to this, then what would this load be at BB prime? The total load now, if I enter this lumped element at BB prime, is going to be the series combination of these 3 elements, R, L, and C. Okay. And then the reactive part of this load, which is that, is going to take this form. Do you agree? Yes? Okay. So now I can check, I can choose C. So I make that 0. That's my goal. If I put this equal to 0, then I put the reactive part of this equal to 0 here. Then I can find a value for C. And I know, in fact, if I also consider, I don't even have to find this by itself. So if I can conserve a little bit of computations, I just write that as 1 over omega and whatever the imaginary part is of the load. So practically I put it here and I find that a C of 0.5 picofarads will cancel my inductance completely at the frequency of 10 gigahertz, which is now called the design frequency because I'm designing there for only that frequency, all right? So indeed, if I put now, see, I have not used the Smith chart because this is easy. If I can put this C there to cancel that, then what is left is only real and is this. So what is left, therefore, is this one. So now I can use a quarter wavelength transformer, which means I can choose my length to be a quarter of a wavelength. I still can choose it. I cannot choose it not. I have to derive it, all right, from here. And then I find that if I put this capacitor of 0.5 picofarads next to the load, and I'm not suggesting here that that's the best solution because it's not always practical to place a capacitor in front of the antenna, all right? But let's assume here is theory, whatever, you can do whatever. So if I put this capacitor there, then, and I make this total at the load at VB primary, and then I use a quarter of a wavelength transformer with this kind of a characteristic impedance, and then I can have a total match here, so I can make the input impedance here to be equal to this, which is 50 ohms, equal to R sub S, which is 50 ohms. So practically through this approach, I make this one to be 50 ohms. And therefore the question to this is yes. All right. So now we are going to one step higher. Can you match this antenna using a transmission line plus a stub? What does that really mean? Okay, I will show you what it really means at the end, so you remember. A stub is a distributed element. Let's assume that in my design, I cannot use lumped elements. All right, so now I go one step higher and say the only thing that I can do is to use sections of line because I can print them, but I cannot use these lumped elements because I have to place them there. And if my design is layered like this, then I cannot squeeze, if I have a capacitor sticking out on the surface of one layer, I cannot put another layer on top if I needed to. So there are possibilities. The previous design is called hybrid design, where we use distributed and lumped elements. There are hybrid designs at low frequencies, but this one for high frequencies, we don't use lumped elements. So this is the second approach. So this one is asking me, can I go on this transmission line and put anywhere a stub like this? It could be short or it could be open at the end. All right, I can choose. But can I use one like that to be able then at this point to make that 50 ohms? And if I use it, where am I going to place it? All right, am I going to place it next to the antenna? Am I going to place it somewhere else? So these are the questions, but visually, it looks something like that. A stub can be placed either like this, which we call series, or it can be placed like this. You will see it in another example, which we're going to do on Friday. That is called a shunt stub, a series and shunt. All right, but this is a series stub the way I did it. You have a choice again. Now, designs are not only one possible solution to a design, there are multiples. So now, here we are going to do, whenever you hear stubs, whenever people are asking you to do a match using only sections of transmission line, then immediately you go to the Smith chart, because if you try to do it using only the equations that we have, you can write equations for everything, all right? It's going to become so complex, and so difficult to solve because you're going to have an equation that is going to have an unknown inside the hyperbolic tangent. And then you will have to do it in the computer, and then you lose also the sense of the electronics, all right, of what you're trying to do physically. So the Smith chart is the best. Now I will remind you. Remember, I told you to feel. Do you remember how to read the Smith chart, you guys? Okay. The first thing we want to do on the Smith chart is to go and find. The first thing we need to do is to go and place this point, ZA, which is our load. We want to find this point on the Smith chart, all right? This. You remember what I said? On the Smith chart, you have to normalize impedances to Z0, and I will use in this case, see now I'm selecting to use a Z0 equals 50 ohms. So whenever you do not use a section of quarter wavelength transformer, all right? So it only in the quarter wavelength transformer, the characteristic impedance is specified by the square root. In every other solution that does not involve a quarter wavelength transformer, then you are free to select the characteristic impedance of the sections of your lines. Yes.
Is there, when designing, is there generally a good number?
Yes.
It's kind of a starting point.
50 ohms.
50 ohms is a good start.
Yes. 50 ohms for most lines. There are specific line architectures that maybe a 50 ohm is difficult to make. So you're looking at 80 ohms maybe, but they will give you, you will know from your design architecture. All right, so but 50 ohms for us is what we are going to use as the standard. So the standard here is 50 ohms for example. Okay. So we normalize the antenna impedance with respect to 50 ohms. And that is shown here. All right, and then we need to find it on the Smith chart. First thing that I do on the Smith chart. You see this point, this one shows where I found this impedance. How did I find it? What is my impedance normalized? At ZA is 2, real part 2, imaginary part plus 0.6. For 2, I'm writing the circle, the red one, that corresponds to value of 2. All right, because I read the values on the horizontal axis. So 2 is here, where I have the dot, and then this circle that goes, the red one, that goes through the red dot, is all of the points on this red circle have a real part, which is 2.0, this. Okay, now I still do not know where my point is. So now I'm looking at 0.6. It says that the normalized reactive part of the point of the CA load is positive and is 0.6. So I'm going positive is on the upper half of the circle. So I'm going and I'm reading here around that, and I found 0.6 here and the green dot on the outer perimetry of the circle, the inner circle. And then from there, I draw the green dotted line, which is the part of these circles that goes through 0.6. And then the intersection between the green dotted circle and the red dotted circle gives me ZA. So you see that I saw it here. And at this point, I put BB prime because this is my load at BB prime, all right, at the output port. So to have a visual to connect also visually. So the load at BB prime, which is this, on the Smith chart is here, okay? Now, I'm not going to do that, but in your designs, normally what we do is, at least electronically, after you find this, we don't need the red circle and the gray. Because most of the time, and in fact, when you get used to it, you're going to put the point without drawing them, because then you have too many circles in real designs, all right? And then but I will leave it here for us. We're learning. All right, so now we are at VB prime. Next. You remember where do we want to go? Where is the matching point on the Smith chart? The matching point is at the center. Remember that? That's where it's 1 and 0, 1 real part, that point at the center of the Smith chart, which now I have as CC prime. That point on the center of the Smith chart, the green dot, has a real part of 1 and an imaginary part of 0. Which means that if I get there, at the point where I get there, my input impedance normalized to Z naught is going to be 1, which means my input impedance at that point is going to be equal to the characteristic impedance of the line. What does that mean? That at whatever point that happens on the line, say if here, for example, if at this point on the line, I don't know exactly where this point is yet, but if I find this point on the line, where this one is 1, everywhere else here to the left of the line, the reflection is 0. Remember? And everywhere here, so the reflection is going to be 0 at this point, and therefore everywhere here the reflection is going to be 0 until I come here, which means my input impedance there will also be 50 ohms. All right? When I have a matched line at any point, it's matched at any other point before then, between that and the source. So if it's 50 ohms here, it's going to be 50 ohms there, 50 ohms there, 50 ohms there, and 50 ohms in the front. And then if this one, for those who are on Zoom, if this one is 50 ohms, it's going to be 50 ohms at any other point along this line until I come to AA prime, we're still going to be there 50 ohms. And therefore, if I match it here, then I'm done. All right, so the question is, how do I get from VB prime to CC prime? All right, that's all that I want to do. It's easy on a transmission line, but on the Smith chart, it's not that easy. I cannot go from here there. You cannot move like this on the Smith chart, like radius, along the radius direction. You can move only along the red circle, or in fact, well, if you, or you can move anywhere along this, or if you want to move along a line specifically, you can only move on the constant Vswr circle. You remember when we named the purple circle? We named it the constant Vswr circle. Why did we name it like this? You remember what I said last time? Because on a transmission line, on this transmission line, what did we say everywhere on the line? The magnitude, if the line does not have anything, right? Anywhere on a straight transmission line, the magnitude of the reflection coefficient is constant. Did we say that? If this line were straight without adding anything, any place on a simple section of a transmission line, the magnitude of the reflection coefficient is constant, which means the Vswr is constant. On a simple section of a line, the Vswr is constant. So I can move along this line here, if I can go from here there, on this line, without any obstructions, I assume that I have not added anything there. If I were to move like this on this line, on the Smith chart, that would imply moving along the purple circle. A movement on the transmission line implies movement along the purple circle. But do I move any direction I want? No. If I am at the load and I want to move towards the generator, I move whatever here towards the generator. All right, even if it's a different balance, but it's generator. Okay, so do you see these green arrows? Yes. Because we know the center and we know where we are. Well, no, if you know the radius and if you know any point on the perimetry of the circle, then you know that the radius is this. Yes, if it's a different one up here, then the circle would go like this. All right? So it always has to go through my point where I am. I am here, BB prime right now. That's where I am. That's my antenna. So now I see here that I can move like this. All right, I can move like this forever. All right, if I move from here and I come back to myself, it's gonna be half a wavelength. Remember, the whole circle is half a wavelength. We move from here 0 to coming back here half a wavelength. So a full circle on the Smith chart is half a wavelength on the transmission line, which implies that if I have a load, that's what you need to remember that. If I have a load and I move half a wavelength, if say D were to be half a wavelength, this input impedance would have been identical with this. Everything repeats. Every half a wavelength, all of the input impedance is repeated. It's like this is going to be the mirror image of that. I mean, the image of this, not the mirror, because the image of this. So this is going to be equal to that. And every other point here is going to repeat here for half a wavelength. And then again, when you have another half wavelength, again, you start from this. All right. So any full circle on the Smith chart gives you half a wavelength. Also, you need to remember, if I ask you, without Smith chart or anything, if I ask you, how much is the input impedance when these have a wavelength? What are you going to tell me? No, 0, please. Yes, thank you. CL in half a wave, every half wave. If I tell you that D is a wavelength, how much is that? CL. Still the same. If it's 3 half wavelengths, still the same. All right, so every half wavelength repeats. Okay. It's easy to see it on the Smith chart. So now obviously I'm moving. The question is, I don't want to come back to the same. I want to go here. That's my destination. How do I go there? I can only move along here, or along here, or along here. If I move along there, I don't do anything. I'm going away from this. I'm going a little bit close to that point, and then I'm going away. So that does not help to move on there. I move on the purple, and then I have to stop someplace. But that's where you decide where you're going to stop. Okay. Why did I stop here? Every moment, if I stop at this point and I want to move again, I have to move. The only way to move is along those lines. Every of these ones, the green light dotted lines that you see here, the green large circle, this one, this green large circle, and all of the other ones you have here, like these ones, oops, this one, all of these circles, this one, all of these. And then you have circles like the red one, this one, okay? These are circles that can get you to places. So let's see how many circles, where can I go from E prime? All right, for a second, because I told you you cannot go straight anywhere. From E prime, I can go 2 directions. Either this is going to be the dotted red one is going to be 1, but if I go here and I move anyway like this or this takes me away from this one. See? So, or I can go through this circle that goes through the center of the circle. So I know as I'm moving on the green with the green arrows and as I'm coming around, I know that the only one that is going to get me there at the center is going to be this circle that goes through the center of the Smith chart. And therefore, as soon as I hit it at EE prime, you see, then I'm going along this circle and I'm going to CC prime. So again, the motions I can do. I find my point B. I want to move. I don't move on the red one because it takes me away. I move on the only other one, like any one that I will move on, and there are 2 circles, 3 circles at every point. I don't go at PP prime, I don't take the red one, dot it, because it takes me away from CC prime. I don't take the green dot it because also it takes me away. But I can take the purple as soon as I find the one that goes to CC prime, and then I get back. It's like taking ways to go from one place to another. And there are buildings here. You cannot go over, all right? So it's like you have to find the right roads to go. And you can only go this way, or this way from B. So I choose this one because then I can cut this one and go there. Okay. So what does that mean now? Okay, I decided what I'm gonna do on the Smith chart, but now I want to understand physically what that means. I know that as I move along the purple circle, practically I move along the line. All right. So where is that? When I move on the, let me see. I have the E prime there. Okay. So you will read all of the details. I have multiple details for you to go through this exercise, and I want you to go through it. So when I move along the purple circle, I move to a place on the transmission line. Here, I move to the point E prime, which is here, I would say, is somewhere here. Very close to CC prime, all right? E prime. So I move very close to that point. Why do I have CC prime differently? Because we are going to insert something there. But I move there until where I stopped. You see, I stopped on the circle at the point E prime. And then I read what my impedance at E prime is. Is it clear? Let me see. E prime. So I read this impedance, all right? And then I find the normalized while I move from there. The only thing that happened, I moved on the transmission line, but my impedance in the new location, which is right here, has changed. My impedance at this point is here, and then put it there. All right. My impedance at this point, I can find it from the Smith chart. So how do I find the impedance at this point? The real part is from here, so it's 1. The imaginary part, I go along this red dotted line and I measure it here. And it's 0.7, it's 0.85, excuse me, it's 0.85 somewhere. But it's negative because I'm in the lower half. So it gives me this. So I went there, but I still am here. I'm not there. So you remember I have to do the last thing. That last thing tells me that to go from E prime to CC prime, my real part the same, but I have to change my reactive part, because if I make this reactive part equal to 0, then I go practically here. So that's what it tells me here. And then we come right there, all right? Where I have now this, and I'm here, but I still need to find out what I'm gonna do and something else at this point to be able to make that to be Z naught. That's what we're trying to go to the center of the chart, all right? So now is where I say, well, you know, if I could do something here, cancel out this part, the minus J 42.5 ohms. And then what I would like you to do is to read the rest because I'm going to do it next time, but I would like you to read the whole problem to see exactly how I'm going to put, I will show you how we are putting this short or open-ended stub. Now, the whole thing is here. I want you to read it, not design example, only that first problem. For Friday, I'm not going to give you anything else. I'm not going to give you an exercise, but I want you to read this problem. And before we start on Friday, I'm going to give you a quiz, a simple quiz to see whether you read the problem. Because I will not continue after that until I make sure that you understand this problem. You have seen it, all right? Get it? Please read it. I wrote it to any possible extent I could in details and try to see whether you understand it at least. All right? Thank you.